Space, the final frontier. But how do we portray space, something that is essentially emptiness? That dilemma has led to a lot of misconceptions about space among astrophotographers. The main one that comes to my mind is the myth that space isn't black. Now, all space contains some background electromagnetic radiation, which you might say is a form of light. But it is so dim that sensors have had to be sent to the far side of our solar system in order to detect it. To our human eyes and to our cameras here on Earth, space is as black gets. Yet, within the realm of astrophotography, there is this persistent myth that space isn't black. Today, I'm going to show how I think that myth started. And I'm also going to show how space, which is technically devoid of matter and devoid of light either reflected or emitted, is nonetheless also desirable signal. In other words, we'll define signal as increasing certainty of information, regardless of whether or not that signal is accumulated information carried by light or the absence of light. Signal is ultimately certainty of what is there, and in the case of space, what is not there. Now, undoubtedly you have noticed that I've been showing you images and clips of Messier 82. I shot this image last January and February, over 7 dark nights, and it consists of 37 hours of integration time. It was actually a lot longer, it was closer to 50 hours, but 37 hours after culling and grading the subframes before stacking them. And we're going to use this image because this is a great deep field image, portraying not just Messier 82, but galaxies and quasars billions of light years in the far distance. And there's IFN all around this galaxy, and deep, dark space between the IFN and those various deep field objects. Now I shot this image at the Sky Story Observatory beneath very dark skies around Bortle 1.5, using a Player 1 Aries M camera with CWO LRGB filters, which, despite their low price, are excellent filters. I've been using them for years and honestly haven't seen any reason to replace them. But to illustrate space today, I'm only going to use the luminance information from the first 6 nights. When you shoot through a luminance filter onto a monochrome camera sensor, it captures all the light, aka information, that's available. Over the course of those 6 nights, I shot a total of 852 luminance subframes at 60 seconds exposure time. I'm going to stack the first night's information, which amounted to 105 subframes, then nights 1, 2, and 3, which amounted to 280 subframes, or almost 3 times the amount of information from night 1 alone. And then I'm going to stack all 6 nights' 852 subframes, which is about 3 times again the total information from nights 1, 2, and 3 combined. So in other words, the night 3 master will have 3 times the information of the night 1 master, and the night 6 master will have 3 times the information of the night 3 master, and 9 times the information of the night 1 master. Before we begin, please bear in mind a couple things. I'm aware that the coloration of Messier 82 here may be different from the intense reds of the ejected gases to the galactic north and south of this galaxy you're used to seeing in other images, particularly narrowband images. This image was shot from dark skies with LRGB filters, which capture more information more quickly and capture the full visible spectrum of light. So the coloration of Messier 82 here is much closer to what we would see were our eyes able to perceive Messier 82. And the other point is, I could easily have altered this and made those ejected gases bright red, but it's artificial, and as I've talked about in previous videos, I really tried to avoid what I consider to be photographic traps, such as the use of hypersaturation and massive unnecessary color transformation just for the sake of being eye-catching. To me, these objects are amazing and beautiful enough just as they naturally are, so let's go ahead and get into the meat of this video. For an apples-to-apples comparison, I prepared the information from all nights in the same way. The only calibration frames that I use, since I'm using a modern camera sensor that doesn't really need dark frames anymore, are bias frames and flat frames. I only shoot new bias frames at the beginning of winter and the beginning of spring, so each night's information has the same bias frame. Among the flats, all red, green, and blue flats were removed, not because they would make any difference to the stacked masters, but just to speed up the stacking time. They were unnecessary since I'm only stacking the luminance images, so only the luminance flats were left in the stack. And each night's information had its own set of flats, which I shoot first thing in the morning after imaging all night. Likewise, among the lights, all red, green, and blue lights were removed. The subframes were shot as fits, visually inspected for obvious problems such as satellite trails, airplane trails, and cloud blockages, and some of the more unique problems that I get living way back in the sticks such as I do, such as the possibility of an owl choosing to perch on the telescope. Then the files were all run through the subframe selector, where they were graded for factors such as star counts and sharpness, and transformed into XISF files. Finally, they were stacked in PixInsight's excellent weighted batch preprocessor. All stacking used the exact same methodology. Since these materials were stacked for educational purposes and I didn't need the absolute best outcomes that I normally would look for if I'm developing an image to keep, I used the fast integration option, though I also selected the more time-consuming maximum quality preset. I will add a side note here that while people often tell me that they do not like to use short exposure subframe times because stacking takes a long time, I want to point out how long it took me to stack all of these sets of data. Stacking 105 subframes took 4 minutes and 25 seconds. Stacking 280 subframes took 4 minutes and 56 seconds. And if you're wondering why there is so little difference in the time between them, it's because a huge part of the stacking time was eaten up in processing calibration frames. And stacking 852 subframes took 19 minutes and 33 seconds. Subframes shot with a 1-inch sensor like you get on the Player One Aries M occupy about 18 megabytes each. Doubtless, if you're using a much larger sensor, your subframes would be bigger and stacking would take longer, but to me, any way you look at it, with modern computers, the process is so fast it hardly matters. I mean, let the computer stack and go do something. Go watch a favorite show, go canoeing, go play frisbee with your dog. In a few hours, the stacking will be done and you'll have great images to work with. Alright, let's take a look at our 3 stacked images. We have Prox or Process 105 for the one that has 105 minutes of integration, Prox 280 for the one with 280 minutes of integration, and Prox 852 for the one with 852 minutes of integration. To keep the stretching approach on each image consistent, I'll stretch them using the screen transfer function. And then I'll fix the screen transfer function stretch onto each image by applying the stretch to the histogram and then applying the histogram to the image. Now in truth, there's also another reason why I'm using the screen transfer function to do the histogram stretch. And it's to illustrate that, while it will give us definitely a controlled and consistent stretching method, how it relates space is going to be deceptive. We'll come back to that later. I'll just rinse and repeat this process with the other 2 images. This yields 3 results that look like this. Let's take a close look at these outcomes. Now, my biggest concern in trying to present this information is that YouTube is terrible when it comes to portraying darks. Its video compression does not differentiate blacks very well, so it compresses them badly. On my photo editing monitor, which uses mini LED technology, the difference between these images is clear as a bell. But depending on your monitor, and especially depending on YouTube, you may not see the difference so well. I will upload these 3 images to the SkyStory Astro bin so that you can compare and contrast better there as well. However, note that the internet also imposes its own very backward compression, which tends to crush blacks too, not as badly as YouTube does, but it still happens. The image on the far left is the one that has only 105 minutes of integration. Compare it with the image on the right, which has 9 times the integration. The detail within the cigar galaxy is far more defined in the right image, and M82 is surrounded by many, far more distant deep field objects, quasars and galaxies hundreds of millions to billions of light years away. And in the image on the right, they show up clearly and crisply. But especially note the quality of the space surrounding M82 in the image on the far left and the far right. IFN appears here and there, making some of the space paler than other areas. And the image on the right, with 9 times the integration as the image on the left, portrays that space better, clearly defining areas with IFN versus empty areas, and portraying both with clarity. Let's go in closer and I'll illustrate this further. Watch what happens with both dark and light areas within the images as we progress from left with low integration time of 105 minutes to the right with very high integration time of 852 minutes. In the leftmost image, the surrounding space is quite dark and might appear to be cleaner, but notice that there is not nearly as much detail in the cigar galaxy showing, and also far fewer extremely dim stars and deep field objects in the background. In the middle image, we have acquired more deep field objects and the surrounding space appears to be a little brighter. And in the rightmost image, with 9 times the integration of the leftmost image and 3 times the integration of the middle image, We have not only revealed far more structure in the cigar galaxy, but we have far more deep field objects showing, and those objects are more defined, brighter, crisper, and clearer. And note that these are just the raw images. I haven't run any kind of sharpening application on them and no denoising. As integration time was added, the stacker became more certain about where light was and wasn't. With only a little bit of integration, it has very little information in particular on the fine structure of the cigar galaxy, and in particular, it has very little information on those deep field objects in the background, which can be billions of light years away. As more integration time is added and the stacker adds the information, it assesses the probability that a bright pixel appearing here and there as photons are caught actually does represent consistent or real signal. So as integration time is added, the stacker becomes more certain that is real information and portrays it as a visible object. Thus, in the rightmost image, we can see far more deep field objects, and the space is brighter because the stacker is certain that there's actually light emanating within that area of space. But what if we take a look at a very dark area of this image? How will the stacker respond to that? Let's look at the dark region right up here above the galaxy. You see the exact same progression here. Extremely dim, distant stars and deep field objects become sharper and brighter as repeated photon strikes recorded in the sensor in each subframe lead the stacker to become more certain that there is indeed signal and not noise in that area. The black, random, changeable space in between the signal becomes more filled out in the middle frame with 280 minutes of integration, and very filled out in the right frame with 852 minutes of integration. As the stacker becomes more and more certain that that is just space and there is nothing there, the region is presented more smoothly. But after the stacker becomes more certain of what is space, the screen transfer function, as we'll see, misassigns brightness to that space, misrepresenting it, giving a false impression that space isn't dark by misinterpreting the growing certainty of the empty space and relating it as gray. I'll illustrate this even further. Let's take a look at an even darker region of space further away from the cigar galaxy. Just below the middle and far to the left of this image, there are two extremely distant galactic clusters, hundreds of millions of light years distant. Let's zoom in on those and take a closer look. Notice the opposite progression is happening here as we look from the left image with the lowest amount of integration time to the right image with 9 times the amount of integration time. The left image with 1/9 the integration of the right image appears to have brighter space. But how can that be? Those objects are extremely distant and extremely faint, and this region of space is very dark. So why would the space in the left image, where there is only 105 minutes of integration, appear pale? The answer is because there is so little information, there is much more noise, and the screen transfer function is artificially elevating the brightness of that noise. The middle image has 3 times the integration of the leftmost image, so there is less noise in it, making its space appear a little darker. But the space regions still appear bright because the screen transfer function is artificially stretching the histogram, making both space and noise appear brighter than they should be. And the rightmost image, with 3 times the integration of the middle image and 9 times the integration of the leftmost image, has far less noise. Nonetheless, the appearance of the space is brighter than it should be because, once again, the screen transfer function has artificially lifted the histogram, making both space and the noise in that space brighter than they should be. In other words, whether there is a little or a lot of information, this automatic histogram stretching method will misrepresent both the space and the noise within it. And if you develop this information even further, the deception gets worse. I'll show you. Here are the same images, but they've been deblurred and denoised with the blur exterminator and noise exterminator, following standard procedure. I undid all transformations and ran the blur exterminator on the masters, then used the screen transfer function to do a histogram stretch in each of the masters, then ran the noise exterminator. Notice how the brightness of the space is the same in each of these images. The space in the leftmost image, with its mere 105 minutes of integration, looks bright, gray, and pretty much the exact same as the image on the right, with its 852 minutes of integration. This is because the noise exterminator has simply averaged the differences in brightness between the noise and space, evening everything out, which is how it smooths out the appearance of space. And that part's fine, that's what denoising is. But then the screen transfer function, a histogram stretching script, deceived us as to what that space looked like by creating an unrealistically bright black point. I'll show you how. The screen transfer function is actually misrepresenting the black point when it applies its histogram stretches to the images. In the images above, I've cloned Prox 105, Prox 280 and Prox 852. And now I'm going to stretch each one of them with a screen transfer function. Now I'm going to show you how the screen transfer function is misleading regarding the actual appearance of darkness. And I don't like to use scripts because I like to know how and why the tools are operating to avoid problems like this, but I'll bet if people are using other scripts due to their stretching for them and they're coming out with the notion that space isn't actually black, this is why. I've selected Prox 105 all the way on the left with 105 minutes of integration and applied the screen transfer function to it. And now I'm going to show how the screen transfer function is handling its light curve. The little caret at the base of the histogram represents the black point as established by the screen transfer function. It's starting more than 2.5 lines up the light curve, way up the light curve, heavily and artificially brightening the space. Now, let's look at the middle image with 280 minutes of integration and see how the screen transfer function has stretched its light curve. The screen transfer function starts the stretch in the exact same location, establishing a false black point way up the light curve, giving the impression that space is gray, creating the exact same false impression about what space should look like. Now let's see what the screen transfer function does with the light curve for the image all the way on the right with 852 minutes of integration. As you can see, it does the exact same thing with this light curve. No matter the quality of the information, no matter where in the histogram the black point actually starts, the screen transfer function always presents a stretch that heavily clips the black side of the light curve, as well as starting well up it, giving space a false minimal value so that it appears as gray rather than its true darkness. This profoundly adversely affects how space appears in images, making black, empty space appear as if it is bright, as if it is gray. Now, I'm going to do a far more accurate and truer stretch, beginning where signal starts on the light curve, thereby reflecting a truer black point, or in other words, the actual darkness that should be portrayed within any given image. All I'm doing is having the black point begin at the beginning of the light curve and placing the midpoint caret at the end of the light curve, where it comes back in touch with the base of the histogram again. This gives a much truer representation of the data, showing space as dark and the objects within it as brighter. And with a proper stretch, we can see that's going on here. The image with 105 minutes of integration on the left, even cleaned up with the blur exterminator and the noise exterminator, portrays the space as brighter because the false illumination that is noise is being mistaken for part of the space, artificially lightening those areas that should be presented as dark, even near black. But at 280 minutes of integration, objects versus space are becoming more sharply contrasted, and at 852 minutes of integration, those extremely distant deep field objects hundreds of millions to billions of light years away are showing up more clearly, while the space is darker still, because all of these samples or subframes allow the stacker to establish a much greater degree of certainty regarding what is space versus what is object. So as integration goes up, the sample becomes larger, certainty becomes greater, and that means the signal becomes clearer, and the space around whatever objects we are imaging becomes cleaner, with less noise, allowing it to show up with clarity, and without the obscuring brightness of noise scattered throughout it. And fundamentally what this means is that the absence of light is as much signal as light is, because, as stated at the beginning of this video, signal, information, is not light. Signal is certainty. A certainty that grows with more samples that happen through greater integration and shooting more subframes, creating ever more certainty in terms of what is actually the appearance of photons here and there on the sensor, and where photons are absent here and there on the sensor. For very bright deep sky objects, this won't be terribly noticeable, but if you're imaging fainter deep sky objects and deep field objects like I often do, this becomes very important. Every photon that lands on the sensor matters, as well as every place where photons don't land. They contribute over long periods of time to building certainty, and that certainty resolves the signal to greater and greater clarity, making for better and better quality images, and even meaning that integration time not only improves the quality of the deep sky objects that you're trying to shoot, but the quality of the space surrounding those objects. And as we have seen, greater integration, properly stretched, also indicates that space is black, and the myth that it isn't has most likely evolved from overly trusting certain stretching scripts like the screen transfer function and doubtless others. And there are doubtless some other factors that played into the development of that myth, such as during much of the time that digital astrophotography was developing, IPS monitors were mainstream, and IPS monitors are really terrible at portraying blacks. But these kinds of monitor issues are topics I've covered in other videos. I think these concepts are counterintuitive. I believe that intuitively we tend to think of light as information, therefore signal, and we probably overlook that we also need to consider the integration of space in order to develop clarity in our images. Because the absence of light is also signal. And whatever we do, we should not be overly trusting of scripts or AI to do our thinking for us in the development of our information. Otherwise, mistakes in the portrayal of the information in our astrophotographs are inevitable, just as we saw in the way that space is falsely portrayed by the screen transfer function, no doubt contributing to the myth that space isn't black. If you have any thoughts, questions, or even objections, please leave them in the comment section below and I will get back to you as soon as possible. Thank you for watching, and as always, have a blast doing astrophotography and get out there and shoot the sky.